Hello, welcome to Video Synthesizer Basics Part 2. I hope you enjoyed Part 1, and if you haven't watched Part 1 yet, I suggest you do. Just stop this video and go back and watch Part 1 because there's some very important things in there. If not, you can watch this video through to the end and then go to Part 1, but make sure you watch Part 1 because it's very important for you to understand how diagram 3 works. So just wanted to mention that. Now, before I show you diagram 3, I want to talk about some things. First, in video 1, I forgot to mention that on December 21st, 2015, I built my second working prototype where I synthesized 240 volts AC from 120 volts AC. I was very happy with that. I lit up two 60-watt light bulbs with the current just needed for one. And I'll explain this how this all works and with diagram 3 when I show this to you. Now, 240 volts, I should mention. Okay, say you're using it to apply voltage to a load. Whatever the load is, 240 volts is twice as dangerous as 120 volts. So be careful when you work with this because it's twice as dangerous if you get electrocuted. But why I'm mentioning this is because in some future videos I'll be showing you how to make this very, very safe. Actually got about 3 methods, and I'll show you how to make this just as safe as the 120 volt system. 120 volts is used in Canada. I think it's maybe 110 volts in America. I'm not sure. And we use 60 cycles per second in Canada, or 60 hertz. And down there in some places it might be 50 hertz. I'm not sure. Things change. And also, I have a method. If I'm right, the voltage synthesizer will make it so that electricity is even safer than it is now using the 120 volt system. And this is a wonderful benefit of this voltage synthesizer. It's going to have so many benefits and potentialities. It's just enormous what can rise from all this. So it's really good. And also in my prototype that I'm going to show you probably in the next video, because I like to take a few breaks here. And I don't use the ground wire. What I use is 2-prong plugs on the end of my extension cords. And I do this because it just shows it's easier to explain without the extra wiring, and the simplicity of it is just simpler. And in my diagram 3 I don't include the ground wire, but I suggest you use the ground wire. Connect it, use the 3-prong plug and connect the ground wire to your electrical boxes. Have them mounted on a base, of course, a plastic light base to screw your light bulbs in. Don't use pigtails because there's no ground on those. And oh, excuse me here, I gotta pause. Oh, I paused it, but I guess it didn't pause. So sorry about that. I had to plug in my charger because I was at 8% left of battery power. So sorry about that. But back to the grounding wires. You can use a green insulated wire or a bare copper wire. But if you're using an oscilloscope to measure the voltages, then it's good to have a ground wire so you have something to ground that ground clip onto when you measure with your oscilloscope. And so it's just good to have that. But it's not absolutely necessary to use the ground clip of an oscilloscope, because you can put the probe tip anywhere in the circuit and it'll show you the voltage at that point, which is really good about oscilloscopes. But okay, now as another safety precaution, I want to mention when you try to measure the voltages of something in a circuit, you can either use a voltmeter, an AC voltmeter, or your oscilloscope. Now, you got to keep a clear mind here. What are you using when you're measuring these voltages? Because it's easy to think that your oscilloscope is a voltmeter. And what you'll do, you'll put the probe tip on one wire, and then you'll put the ground clip on the other side, say on the other side of the load resistor, and you're thinking it's a voltmeter and it's an oscilloscope, and if you put it on the hot wire or even the neutral wire, you're going to have a big spark. You know, electricity is going to go through that ground clip down into your oscilloscope, down the ground wire, but it shouldn't harm your oscilloscope, but I wouldn't, risk it. So make sure you keep a clear mind when you're doing this. What are you using? The voltmeter or the oscilloscope? Now the voltmeter has a positive and a negative, or red and black probes, so you don't really have to, there's no ground clip on that to worry about. You just connect the voltmeter in parallel with whatever you're measuring. Okay, enough about that. Also want to mention that link that I showed you in video 1. I put that in the description. It shows underneath the video, so you can just find that there and click on that, and it'll go right to the weepo.int website and show you my publication that I did. That got published on May 16th of this year. And I'll put it in the description underneath this video too, so you can always look at it there. And I hope to be adding more pages of text and some more diagrams to that later, that publication with the World Intellectual Property Office. And I emailed them, asked them about that. I hope they don't charge me some more money for that, but they probably will. I hope no more than $100, $200. I spent a lot of money on this already. And maybe I should talk about transformers. All transformers are actually isolation transformers, whether step up, step down, or center tapped, or I don't know if there's any other kind, but well, there are, but there are different arrangements. And but they're all isolation transformers, because what they do, they're actually transducers, but what they should be called is more like transducing or transducer doublers or something. Because first they transduce electricity into electromagnetism through the primary coil, and then the secondary coil actually transduces electromagnetism back into electricity at the output of the secondary. So they're actually a double transducer, is a better word for it. So I just want to mention that, but the isolation transformer that I use is a 1-to-1 ratio transformer. The number of coils in the primary equals the number of coils in the secondary. So if 120 volts goes into it, 120 volts comes out. If 5 amps goes into it, then 5 amps comes out. So if you're using a 10-to-1 ratio transformer, 120 volts goes in and 12 volts comes out. But as you do this, if say, I can't think of a good figure to use, but the current available at that 12 volts from the secondary is a whole bunch more. The ratio of it, you got to figure out the ratios, the proportion, just use the proportion formula, and you can figure out how much current is going to come out of that secondary. Because, 120 volts drops down by 10 to 12 volts. So if you got, say, 1 amp going into the primary, then I think you can times that by 10. You'll have 10 amps of current coming out of the secondary. I think that's right, if I'm correct. Now, isolation transformers. Now, they're 1-to-1 ratio, okay? Now, the only thing they really use them for is TV repairmen used to use them a lot back in the 70s and 80s and maybe later. But back then, TVs were a lot different than they are now. And what they basically used them for was when they're troubleshooting a TV while the TV is turned on. They're troubleshooting it. What to do, they plug the cord of the TV into the secondary, the isolation transformer, which is plugged into a duplex receptacle. And what that does, it protects them from any power surges that could go on in the electrical lines. And it protects not only protects the troubleshooter from any kind of harm that could be caused to him, but also protects the electronic components, the resistors, capacitors, transistors, and all that stuff. It protects them from getting damaged, from having too much voltage going into them. If that happens, then they have to fix that, And it also protects them from thunderstorm activity, because the primary and secondary are not connected electrically. They're connected electromagnetically through the induction that the coils make. Actually, the primary coil makes. It induces electromagnetism to go into the secondary coil. So you have to understand how that works. So, but now these isolation transformers they use, they're big, bulky ones. I'll show you one, the one that I have in my next video, and they're heavy too. But they're really good for something like 1500 watt heater in a greenhouse. But for light bulbs, 100 watt light bulbs, they could be 10 times smaller. That'll be ample enough supply for that. So we need these transformer companies to manufacture these smaller isolation transformers that we can use in the future. And I'm going to have to convince someone to do that, or maybe start up a company and do it myself. Someone's got to manufacture them. If the people, the government that makes the laws and regulations, if they allow us to use this in the future in our electrical appliances and just our lights and stuff in our houses, we're going to have to have a house and set this all up and show them how efficient and energy saving it is, and it's going to really help the environment. It's really going to help the environment. That's why I want everyone to embrace this, because if we don't stop this global warming, they say in 2050 the whole world is going to be underwater because of all the polar ice caps melting. And there's so many people out there in denial that oh, the world's not warming up, that's because they're thinking about money in their pocket, they don't want to stop this pollution that we're causing. And the voltage synthesizer will help that. And I will work with these companies that are going to pose my ideas. I'm going to work with them. I'm going to satisfy them. Okay? I'm going to satisfy them. I'm going to make them complacent, if that's the word. And I'm going to work with them. I'm not a greedy person. I don't want all this money to come to me. I'm going to work with them. I'm going to work with everybody so that they're not afraid of losing their jobs. They're not afraid of living on the streets, out of a job and stuff like that. I'm gonna make it work. Okay, enough on that. Yeah, I'll talk about the speed of electricity after I'm done. Let's get into diagram 3 first, though. Okay, here's diagram 3. Now I just need something to point with here. There's my pen. Maybe this little stir stick will work better. Diagram 3. Okay, here is the one voltage source I was talking about instead of 2. And let's say it's 120 volts. And here's the one parallel connection going to A and B, and then the other parallel connection going to B and C. Let's hold on here. No, actually E and F, I should say. E and F is the primary coil. But C and D is still part of the parallel branch. Okay. Now, here is the series connection that I talked about. I think this pen will be a little better to point at with. B and C is that series connection I talked about. And this isolation transformer isolates, it isolates these two parallel branches, A and B, from C and D. And remember that B is connected to the negative, and C is connected to the positive. So now that they're isolated, they can't short out like I showed you in diagram 1, and cause that short-circuiting danger. Now this isolation transformer does it because the primary coil, which is E and F here, is isolated from C and D because the transformer is not electrically connected, it's electromagnetically connected. So you can't short out through that. Okay, it's like magnetism. The lines of force are magnetism. So it's not connected like wires are connected electrically, but magnetism is not connected electrically. So it's isolated. So now, like I was saying before, if a circuit could think, it would think, oh, there's two sources of electricity here. One is AB and one is C and D. Okay, like two batteries and a flashlight. Okay, 120 volts here, 120 volts there. And that's the one-to-one ratio transformer I was talking about. These lines in the middle here are for center tap, but just ignore those for now. But I'll be showing you how to use that in diagram 5. Now, we've got them connected in series. It's actually a series parallel circuit. And over here is the load. But this time I got two load resistors here, R1 and R2. Now, why do we have two? Because we have 240 volts here, and if we just had one light bulb, pretend these are both 100-watt light bulbs. If we had only one light bulb, there'd be too much electromotive force in there, it might damage the light bulb. So we got about 200-watt light bulbs here because, maybe put this a little closer, you can see a little better. two light bulbs here because we have the current that we need just for one light bulb, and we're going to pass it through both because we have 240 volts. Now what happens is, let's say this is the hot wire at A. So electricity goes this way first and comes down here over R1. The top one is R1, yeah. And so 120 volt drops over this first light bulb, and it pushes the current that it needs, which is 833 milliamps, according to Ohm's law. And it goes through here. But now we still have another 120 volts because we got 240 volts in total. And what it does, that extra 120 volts will drop over there. And when it does, drops over R2, it pushes that current, 833 milliamps, through R2. And then it goes over here to the, I guess you could call that neutral. The neutral. And actually it goes up here through the secondary coil, up to B, and then over here to the negative of the source. And remember, it started at the positive. So there you go. And then when the hot wire changes neutral, it just goes the other way around. And the neutral wire changes to hot, it goes the other way around like that. Okay? But now, the fantastic thing about this process is that, okay, from Ohm's law, a 100-watt light bulb, the resistance measures about 144 ohms. But now we got two here. So add those together, that make 288 ohms. So what that should do is cut the current in half. So instead of having 833 milliamps, it should be about 416 milliamps. But what the amazing thing is, it's kind of hard to explain how it works, but it's like this one voltage source sees this load resistance and it puts out 416 milliamps. And this other voltage branch, CD, it also sees this total resistance. So it puts out 416 milliamps. But then you add them together and you got 833 milliamps, which is how much you need for one. So it's all you really need for one. But because you got 240 volts, you have the necessary voltage drops. 120 volt drops over there, and 120 volt drops over there. So it's really amazing how this works. So if you take your voltmeter and you put one probe at J and the other probe at well, no, that's G up there and J down here. Okay, you're going to have 240 volts. Now, if you put one probe at G and one at H, you're going to measure 120 volts. And then if you put another probe at I and one at J, it's going to measure 120 volts. So that proves you have the necessary voltage drops to push that current all the way through there. Okay. Now this is the problem with batteries also. They put the current, a 12-volt battery will put the voltage over a device, but then once it goes through the device, there's no voltage left to push it through anything else, and then it doesn't even have the voltage to push it back into the battery. And that's why batteries drain and they have to be charged. So this is going to be really important for electric cars in the future. And I'll talk about that and how all the benefits of the voltage synthesizer is just amazing. And it's very exciting to know all this stuff. Okay, now I think I explained everything I need to explain about this. So I'll just pause this for a minute. Okay, that's all I wanted to really explain about diagram 3. So my next video I'll show the working prototype I have. But I want to talk about the speed of electricity and the wavelength of a 60 cycle or 60 hertz signal. So back to diagram 3. This source is 120 volts from your wall outlet, and it's 60 hertz or 60 cycles per second. And this one sine wave where it goes up and then it comes down, that's one wavelength. And actually that's one cycle. So when it goes up, that's half a cycle. And when it goes down, that's the other half cycle. One's positive and one's negative. So what happens is it changes kind of like twice in one cycle. Changes direction. The current changes direction. First goes this way, and then it goes that way, sort of thing. So actually what it's doing is, if I'm right, it's actually changing 120 times per second. So that's pretty fast. But the speed of electricity now, what do you think the speed of electricity is? I wanted to clear this up because a lot of people think that the speed of electricity is the same as the speed of light. Now, that is false. Now, I was, what's the word? I can't think of the word to use, but I was wrong, thinking wrong about that for about 20, almost 25 years. Back in 1989 or 90, I read, when I went to technical school and I took electronic communications, I was reading in a textbook or something about the speed of electricity, and they said it was 300,000 meters per second. And I remember that figure from physics, because they said that in physics, but. So I assumed that, oh, that's the speed of light. But no, it's not. The speed of light is 300 million meters per second, or 186,000 miles per second. And the speed of electricity is 300,000. This is a rounding off figures. Speed of electricity is about 300,000 meters per second, and the speed of light is a little less than 300 million. It's about 299 point something million meters per second. And think of it, photons, or should I say electrons, don't travel at the same speed as photons do. The speed of light is for light or electromagnetic radiation, like microwaves and radio waves and stuff. That's what that's for. Now, electrons, they travel through copper wires, okay? And they can't travel as fast as photons, because photons go through the vacuum of space or through the air or through glass or water. Now, when they go through water or glass, the speed slows down slower than it does through air, because it's a denser material. Now, electrons, they go through copper wire, or maybe silver or gold or other metals, and there is a slight difference between the different conductors. but copper is used because it's the cheapest material that they use. But in computers they use silver and gold more. And so I just wanted to clear that up. So actually, now there's this formula here, down here, to calculate the wavelength. The wavelength, this is a symbol for wavelength, equals c divided by f. C is the speed of light, and f is the frequency. So for the speed of light, you'd use 300 million meters per second. But you got to know the frequency of the light. Say you're using the laser light 630 nanometers, we put that in there. That's red light. And then you could calculate the wavelength. So if we thought that the speed of electricity was the same as speed of light, and we put 60 hertz down here for the frequency, the wavelength would equal 5,000 meters. And I thought, gee, that's really long. So I was wondering about that. So what you got to do is put 300,000 meters in here instead, and 60 hertz here. Then the wavelength of a 60 cycles per second signal is 5 meters in length, which makes a lot more sense because the speed of electricity is about 1,000 times less than the speed of light. So, to show you that here, if you can read that, what did I write there? Yeah, just the speed of it. So I just wanted to clear that up because there's so many textbooks out there that say, electricity and electronics, and it operates at the speed of light, but that's false. And but that is really good news for things like nanotechnology and robotics, because you can use light to speed up circuitry ahead of time. You got electricity going down a wire, a circuit. If you use a diode to create some light, it can travel down the circuit even faster. In robotics, it would enable robots to have a quicker reaction time. Like things would switch off, on and off faster. And they should be using that. I don't know if they know about that or not. But okay, I guess that's enough about that. And this video is 33, just over 33 minutes long, and I didn't think it would take that long. So I'm going to have to show you the prototype in the next one. So I'll stop now and continue later. So I'll see you then. Thank you very much for watching.